Okay, now let's look at this question. A projectile is fired straight upwards from the Earth's surface at the South Pole with an initial speed equal to 1/3 of the escape speed. Ignoring air resistance, determine how far from the center of the Earth, how far from the center of Earth the projectile travels before stopping momentarily. And then what is the altitude of the projectile at this instant? Okay, this is quite a challenging question. First of all, we need to let us use a diagram to show what's happening. Okay, let me use a diagram. Okay, I have drawn the diagram already. Yeah, look at here. He say the projectile is fired from the Earth's south pole, and on the surface, Earth fired from the surface at the south pole. Okay, so south pole. So actually, projectile is projected from the south pole and then go to the top. Go to the top. However, yeah, to make things easier, I just invert it to the top. Yeah. This south pole I just put to the top here, so easy for me to explain to you. Yeah, so actually here is a south pole. Okay, so I just don't want to make things inverted. Yeah, very hard to explain. Just invert, become like this. Okay, no matter how, it's still ejected from the surface. This is the point I want to emphasize. It ejected from the surface. Okay, remember, so ejected from the surface. So now ejected from the surface with initial speed equal to 1/3 of the escape speed. That means, okay, look at here. Here he say escape speed. Okay, but the speed ejected is not escape speed. It's just 1/3 of it. 1/3 of the escape speed. That means here the initial speed is just 1/3 of the escape speed. So that means this speed is smaller than the escape velocity. Smaller than the escape velocity. So, if this projectile is ejected smaller than the escape velocity, it will not escape fully from gravitational pull. It will escape lower than that. It will escape to the lower height from the escape position. Okay? So only it escape with this small 1/3 only from the escape speed. So it cannot escape fully from gravitational pull. Okay, it cannot go to the 0 joule maximum potential energy. Remember, the 0 joule is the maximum potential energy. I hope you still remember. Okay, now the question is, how far is it? How far is it from the center? Okay, how far from the center of the Earth the projectile travels before stopping momentarily? That means this question here, it asks about the R. You need to know the R from the center. This is the R, not the altitude. Altitude is from the surface, but this one he asks from the center. So he need the R. Before the projectile travels before stopping momentarily. What does it mean by this one? Stopping momentarily. That means all the kinetic energy has turned to potential energy. This is the kinetic energy has already all the kinetic energy has changed to potential energy. So this one is all we use conservation of energy. Conservation of energy. Yeah, at the surface it is ejected with high velocity. So at the surface it has high kinetic energy. But when it goes up and up, the kinetic energy turn to potential energy. So when stopped momentarily, that means all the kinetic energy has already turned to potential energy. So no more. So at the height, it has no more velocity. It stopped. Yeah, it has no more velocity, no more kinetic energy. All kinetic energy has turned to potential energy. Okay, so I just want here I already illustrate to you. You see that? For the escape velocity, again, we go back to the concept. Yeah, escape velocity is the velocity at the surface. Let's say the projectile start from the surface Okay, at the surface, the distance of the projectile from the center of Earth is actually radius of Earth. Okay, so if this projectile is ejected with escape velocity, it can go to the infinity distance. The r become infinity, so it can go to the potential energy 0 joule. It can go to the maximum potential energy 0 joule. To free from gravitational pull. Okay, at the surface, the potential energy is because the distance to the center of Earth is the radius of Earth. Because you are at the surface, so your distance to the center of Earth is radius of Earth. Okay, so your potential energy over here, potential energy at the surface of Earth is negative gmm over r. Negative gmm over radius of Earth. You see that? Gmm over radius of Earth, because you start from the surface. If this projectile is ejected with escape velocity, it can go from potential energy negative gmm over radius of Earth. It go to the infinity distance until the potential energy become 0 joule. So the kinetic energy all has turned to potential energy. It can go to 0 joule if escape velocity. However, this question says this projectile is ejected not with escape velocity. It is ejected with velocity less than that, less than escape velocity, with only 1/3 of the escape velocity. So what happened is to the projectile is this projectile cannot go to 0 joule potential energy. It will go to a lower position. It can go to a lower height. So we don't know what's the r here. That's what we want to find out. This is what we want to find out in question A. We want to find this r. We want to find this r. We want to find this r. You understand or not? We want to find this r. So if ejected to this height, yeah, u equal to negative gmm over r. What is this r? This r is distance of this position to the center of Earth. It is this distance. I just want you to understand it is this distance. This is the r we need to find. Okay. So it is ejected. Remember the starcraft? No, the projectile is ejected from the surface. So it starts from r equal to radius of Earth. It starts from r equal to radius of Earth. I go to this position with value r, and we don't know what is this distance. So it is here at the surface. It has kinetic energy. Okay, and then this kinetic energy has turned to potential energy at this point. The difference in the potential energy between these 2 points. So how to find the r over here? We use the principle of conservation of energy. Okay, let me write it down. We want to use the principle of conservation of this one, mechanical energy, because this one we only talk about potential energy, kinetic energy, potential energy, kinetic energy. We don't talk about friction. We don't talk about energy loss due to friction. Okay, we don't okay, I will make it bigger. Okay, yeah, we just talk about principle of conservation of mechanical energy. All the while we just talk about potential and kinetic. Okay, now look at here. We can say the change in kinetic energy, okay, from this position. This is the initial position. Okay, maybe let me write it down. This is the initial, and this is the final. Okay, initial and final. So it ejected from the surface with the speed 1/3 of the escape speed. Okay, it end up here. So we use this formula, principle of conservation of mechanical energy. So the change in kinetic energy will result in the change of potential energy. Okay, so let me write it down. Yeah, so this one we want to find the r over here. So how? So initially it has the kinetic energy because it ejected with this speed, 1/3 of escape speed. So initially at initial position it has the kinetic energy. So we just put half mv square. Okay, half mv square equal to change in potential energy. So we just use the U final minus the U initial. Okay. Because that is the difference in the potential energy between these 2 points. You know, the difference in the kinetic energy result in the, the kinetic energy drop. The kinetic energy drop, the potential energy increase. Why increase? Because it is the kinetic energy turned to potential energy. Okay. So we use this one. Okay. So now let's continue. Yeah. So so half. Okay. This okay. Just maintain as. Let's continue. Okay, this is half mv square and then equal to, what's the final potential energy? It is this one lah. Negative. We put as negative gm m over r. We want to find the r there. Understand? This is what we want to find. This is the r we want to find. And then minus. Remember, the initial potential energy also has the negative sign. So don't forget, put the negative for u also. Yeah. So become negative, negative become positive. Okay. So it starts from the surface initial position. This is the initial position is negative gmm over radius of Earth. Gmm over radius of Earth. Okay. So the kinetic energy has caused the change in the potential energy from initial become final. Remember, this is the initial, and then this is the final position. Yeah, it is the kinetic energy that causes the change. Causes the change from initial to final. All because of the escapes velocity, all because of the kinetic energy. Cause the change from initial to final. Understand? We want to find the R here. So okay, now let us continue. What is the small m over here? I want to ask you, what is a small m over here? This of course is the mass of projectile, isn't it? This of course is the small m here is of course is the mass of projectile. Mass of projectile, right? The small m here, also the m here and the m here. All of these are the mass of projectile, so we can cut that off. Yeah. So maybe let us use. Okay. So this is the mass of projectile. So all you can see over here, all these small masses, they are common terms, right? Common terms you can cut off. You can cut this off. Less one burden. Okay. So and then okay, let's continue. So and then our speed here is using 1/3 of the escape velocity. So we can substitute. Okay, so let's find out our v first. Our v is actually called 1/3 of escape velocity. You still have the equation for escape velocity. You have the equation for escape velocity. Over here, see the escape velocity. This is the formula. This escape velocity also we discussed before. Escape velocity is we bring from the surface to the zero. You see, from the surface we bring to the maximum height, 0 joule potential energy. This is how we find the escape velocity, and this is the formula we get for escape velocity: square root 2gm over r. Okay, square root 2gm over radius of Earth. So we use this formula. Yeah, put inside. Yeah, so we use that formula. 1/3. Okay, escape velocity is, sorry again, 2gm over r, radius of Earth. 2gm over radius of Earth. Okay. Yeah. Given the Earth radius, not given. Never mind. Okay, so we got this already. Okay, this is the one. Okay, this is the formula. It doesn't give us any the mass of Earth, the radius of Earth. Never mind. We just put into the equation first. So this is the escape velocity formula, 2gm over r. Okay. Okay. So we just substitute this one into here, v here. Yeah, because this v is just ejected with 1/3 of the escape speed, 1/3 only. So this v, we substitute with this one. Okay, and see what happened. Okay. Basically, I still waiting to see how this will turn out. I don't know how can it be solved yet. Yeah, but this is my rough idea. Okay, waiting to see whether it works out or not. Okay, so oh sorry, 1/3. I missed out the 1/3, isn't it? I missed out the 1/3. Okay, yeah. So miss out the 1/3. Remember, the speed is not escape speed. The speed is just 1/3 of the escape speed. 1/3. So square. Yeah, it has a square. You see that? V square. So the 1/3 escape speed, I square it. Okay, and then equal to this is gm over r, which we want to find the r, and then this, oh, I forget the negative here. Yeah, negative. I forget the negative sign. Yeah, so be very careful. Be very careful. The negative sign, and then this one is plus, and then this gm over radius of Earth. Okay, so now square it. What do you get? What do you get after you square it? You get, this is 1/9, and then this one become, this one has a square root, isn't it? Just under 3, after square you get 9, but this one has a square root. After square you get a normal square root. So you got this one. Okay, you are free from the square root. You're gone. The square root is gone. And then this one, okay, I just changed the position. This is RE as positive, this one as negative. Okay, now I can cut this one. Yeah, I can cut this one, and what do I get? I think slowly I can solve these questions. This is gm over 9 radius of Earth. Okay. Okay. So, yep, it's correct. Now let's move on. Okay, let's move on. Am I correct? Yeah, I'm correct. So, and then you have here, you have gm over re, and then negative gm over small r. Okay, from here I can cut the common, isn't it? These are the common. Let's cut it off, and let's cut it off. So, okay, what's left? So what's left is 1/9 re equal to 1/re minus 1/r. Okay, so what I will do is so I just transfer this one to the other side. Okay, what I get is this one. Well, 1/r. Okay, this one I switch position, go to here, and this one go to the other side. And this one minus 1/9 re. Am I correct? Yes. Okay, this one go to the other side. Got this one. So this one can be combined, get 9 re here. Yep. Oh, what is this? 19 re. Okay. This one is this one multiply 9. Yeah, multiply 9. This one top is also multiply 9. Okay, multiply 9 below, multiply 9 top, also multiply 9. I get this. This one minus 1. Okay, this is 1/r. Okay, and then following is 1/r equal to this one is 8/9 re. Okay, so what is my r? My r is 9/9 re over 8. What is my radius of Earth? Let's find out. Okay, let's find out the radius of Earth, because it's not provided in the question, the radius of Earth, right? So this value, radius of Earth, you can find from the list of constant provided. So I just refer to the previous question, see if I have the radius of Earth. Yes, it has the radius of Earth. 6.4 exponent 6. 6.4 exponent 6, that's 646. 646, remember? 646. Okay, just do it. So 646. So radius of Earth is 9/8. Radius of Earth is 646. 6.4 exponent 6. Okay, so let's calculate the radius of Earth. Yeah, no, not the radius of Earth. Let's calculate the R, which we want to find. It's exponent 6 multiply 9 divided by 8. So what do I get? Oh, I got the jackpot. It is 7.236. 7.2 exponent 6 meter. Okay. Okay, so that's the answer. That's the answer. Okay, am I correct? Am I correct? Oh no. Yeah, what I think is this answer 7.2 exponent 6. If I compare to the actual answer, is a little bit different. I don't know why. But I'm pretty sure after I check all my steps, they are correct. Okay, so okay, 7.09, but I'm still stick to my answer. Okay, I'm still stick to my answer. So hope you double check. Okay, I hope that if I'm wrong, please comment below. Okay, if I'm wrong, please comment below. I'm still stick with my answer. Okay, so the answer which I feel is correct is 7.2 exponent 6. Okay, you can check my solution whether anything wrong. Okay, so basically how I do this question is I just use the principle of conservation of mechanical energy. Yeah, that means from this position as projected with the speed 1/3. Yeah, isn't it 1/3? Yeah, 1/3 of the escape speed. Okay, so from the potential energy with radius of Earth, it will go to the potential energy with radius r. Okay, radius r. So this is the r I get using the principle of conservation of mechanical energy, and this is the r I get finally 7.2 exponent 6 meter. Okay, now next questions. Just now that one is question A. Now question B, what is the altitude then? What is the altitude of the projectile at this instant? So this question asks for h, is asked for h, altitude. So what is altitude? Actually, altitude means from here to here. Yeah, this is the altitude, the h, the h. So r is actually the radius of Earth plus altitude. Understand? It's radius of Earth plus altitude. So let's find out the h here. Okay. So question B, just now is question A. So now question B, sorry, what is this? So R is I got R is radius of Earth plus the h, which I want to find the h now. Okay, so okay, my R is 7.2 exponent 6. Okay, 7.2 exponent 6 equal to, what's the radius of Earth again? I used just now 6.4 exponent 6. Yeah, 6.4 exponent 6 plus the h. Okay, so let's calculate. Yeah, minus out the radius of Earth. Then that is the answer already. Yeah, my h is 8 exponent. My h is 8 exponent 5. 8 exponent 5 meter. Okay, that's the answer which I think is correct. So is that the answer? A little bit different because I already different from the R. So I still stick with my answer. Yeah. If you think that anything I'm wrong, please comment below. Yeah. Anyway, thank you for watching. Okay. See you.